Specifically, at round T, the central server sends the current global model to selected participant. The participant locally compute a function by running an optimization algorithm with its own private dataset to obtain a new local model. Then they send the model update back to the central server, who will average over all updates to generate a new global model. Although federated learning is capable of generating aggregating dispersed information provided by different participants to train a better model, its distributed learning methodology, as well as the inherently heterogeneous data distribution across different participants, may unintentionally provide a venue to new attacks. In particular, the fact of limiting access to individual participants' data due to privacy concerns may facilitate data poisoning attacks on the shared model trained with federated learning. Backdoor attack is a type of data poisoning attack that aims to manipulate a subset of the training data, such that the machine learning models trained on the tempered dataset make a targeted wrong prediction on any input data that has an attacker-chosen pattern. As illustrated in the figure, the model makes the correct prediction on the benign data. It's the main task. The model makes the targeted wrong prediction on the backdoor data with an attacker-chosen pattern. It's the backdoor task. For an example, any image with a 4 white rectangle pattern on the left upper corner in these images will be classified as targeted label birds. During the training time, the model will both learn the main task and the backdoor task. Instead of preventing the convergence inaccuracy as Byzantine attacks, the purpose of backdoor attacks in federated learning is to manipulate the local models to simultaneously fit the main task and the backdoor task, so that after the aggregation, the global model would behave normally on the benign data while achieving high attack success rate on the backdoor data. Then we move to the distributed backdoor attack. Current attacks embed the same trigger pattern to all adversarial attackers. We call such attacking scheme as centralized backdoor attack. Leveraging the distributed learning methodology of federated learning, in this work, we propose the distributed backdoor attack. Given the same global trigger pattern as the centralized attack, DBA decomposes it into local patterns and embed them to different adversarial participants respectively. In the centralized attack, the attacker embeds the selected patterns highlighted by the 4 colors into the training data, which altogether constitutes a complete global pattern as the backdoor trigger. In our DBA, all attackers only use part of the global trigger to poison the local models. For example, the attacker with the orange sign poisons a subset of his training data only using the trigger pattern located on the orange area. Similar attacking methodology applies to the green, yellow, and the blue signs. We define each attacker's DBA attacker's trigger as a local trigger and the combined whole trigger as a global trigger. In DBA, all attackers only use part of the global trigger to poison their local models, while the ultimate adversarial goal is still the same as the centralized attack, using the global trigger to attack the shared global model. For the fair comparison, we keep the same amount of total injected trigger. In the image dataset, it's the modified pixel for both centralized attack and the DBA. We note that DBA outperformed the centralized attack significantly. There are some examples of the backdoor data. For the centralized attack, they can use the ICLR logo for the MNIST dataset or CIFAR dataset or Tiny ImageNet dataset. But the distributed attacker will decompose the logo into 4 parts and embed them to their local training data set respectively. And we can also decompose the physical glass pattern into the 4 parts. And we can also use different color of the trigger pattern. The attacker ability in federated learning is that they have full control of their local training process. It includes backdoor data injection and updating local training hyperparameters, including local training epoch and the local learning rate. And they do not have the ability to influence the privilege of central server, such as changing the aggregation roles. And they don't have the ability to influence other clients, like tempering the training process, and they can't tempering the model updates of other clients. The purpose of backdoor attack in federated learning, as we mentioned before, is to manipulate the local model so that the global model would behave normally on the clean data samples while achieving high attack success rate on the backdoor sample. The objective of the centralized backdoor attack include both the malicious objective and the benign objective. The attacker wants the global model to predict the targeted label tau for backdoor data and predict the original label for the clean data. In this mathematical formulation, the Poisson ratio is the control. The Poisson ratio controls the fraction of backdoor samples in the local data set. The local data set include the Poisson data and the clean data. And for the image data set, the phi is a set of parameter of attacker chosen pattern. For the image data set, it includes the trigger size, trigger gap, and the trigger location. For simplicity, we set all our local triggers to the same rectangle shape. For the tabular data, there are many columns in the table. For the task like long status prediction, each column is in the table is a feature. We sort these features by importance, and the feature importance can be a trigger factor. We can use low importance features as a trigger or the high importance features as a trigger. And the function R transform any clean data in any class into the backdoor data. And the target label is tau. And then the objective distributed backdoor attack is like this. In the DBA, each distributed attacker independently performs a backdoor attack on their local model. They also include the malicious objective and the benign objective, and there are M distributed attackers. The phi star is a geometric decomposing strategy for the local trigger pattern. Phi star is a local trigger pattern, but not the global trigger pattern. The Poisson round interval is unique for DBA. The Poisson round interval is a round interval between two distributed Poisson steps. For example, if I equal to 0, it means that all the local triggers are embedded within one round, while I equal to 1 means that the local triggers are embedded in consecutive rounds. The scaling factor gamma is used to scale up the malicious update by the attacker. This novel mechanism breaks a centralized attack formulation into multiple distributed sub-attack questions. So moving to the experiments now. To compare the performance of distributed and centralized attack, we evaluate 2 attack scenarios. The first attack scenario is multiple shot attack. Here we are looking at the result from MNIST dataset. Multiple shot attack means that the attacker are selected in multiple rounds, and the accumulative malicious updates are necessary for a successful backdoor attack. Otherwise, the backdoor would be weakened by the benign updates during the average and soon be forgotten by the global model. In order to quickly observe the difference between the centralized and the distributed attack and control the effect of random party selection, we perform a complete attack in every round. That is, all DBA attacker or centralized attacker are constantly selected.
Sorry, Chulin, there is one question from the audience. I'll try to unmute Ali. You can ask yourself.
Yeah.
Okay, the question is, the backdoor samples are available only to malicious nodes during the training? Like, because I understood like you have some benign samples and then backdoor samples, right?
Yeah.
So like, yeah, basically, let's say if it's MNIST or CFR10, whatever. So like you separate some particular like samples as malicious ones, and they're only available to those malicious those attackers, or also like honest nodes, they have also like those samples.
Because the trigger pattern is the attacker chosen pattern, and the attacker designed those patterns. So the backdoor data is only owned by those backdoor attackers. The honest client won't have these backdoor samples.
Oh yeah, I mean, they don't have even the original sample, right?
Yeah.
Okay. Okay, and then like okay, and then in the inference time use like some like those original samples are used and then they are labeled like incorrectly. Is it like this?
During the query, we use the test data set, but during training, we use the training data set. It's two data sets.
No, I know, but basically, yeah, like you use the original like sample, basically, which is those like backdoor samples, and then basically they will be labeled as like what the malicious nodes want, basically, right?
Yeah.
But in the training, no honest node has access to those backdoor samples, like.
Yeah.
Okay, got it. Thanks.
Yeah.
So there is one other question from Kayun. I'll unmute you. Okay,
Hi.
please go ahead.
Yeah, thank you. Actually, I have a question like here. As my understanding, the centralized attack should be only have like one global trigger, right? So, but
Yeah.
why it also have like 4 local triggers? As I see it from your paper, I see the centralized attack also have 4 local triggers. So can you explain this one? Thank you.
No, according to this slide, in this example, the global trigger is decomposed into 4 local triggers. So there is 1 centralized attack and 4 distributed attackers. So if there are 2 centralized attacker, for the fair comparison, there would be 8 distributed attacker. In this case, they will have the same amount of total injected trigger, which means the modified pixel.
Okay, I see. Thank you.
Yeah.
Okay, so it seems that there are no other questions at the moment, so you can continue.
Okay. Let's back to the multiple shot attack scenarios. Yes, we're talking about the evaluation setup. The distributed attackers.
Sorry. There is one extra question from Konstantin. Let me just unmute him.
Okay.
Please go ahead, Konstantin.
Thank you. So my question is, what ecosystem did you use for experiments? Do you use like TensorFlow federative learning or what something another? And how is it 10 agents in each round executed? Is it in local machine or is it distributed setting?
Oh yes, for the hardware, do you mean the computers I used?
Yeah, I mean, for this work, did you simulate everything in a local machine, or you use some decentralized, I mean, some network of the nodes?
Oh, we used local machines.
One single local machine, yeah. Okay.
Yeah. Yeah. In this figure, we have x-axis here to be the number of community runs, and y-axis here to be the attack success rate of the global model for the test data. Let's first test the attack success rate of the global trigger in the global model. It's in the test data, not the training data. We can see that the DBA, which is the black line, converges faster and even yields a higher attack success rate than a centralized backdoor attack. Then we look at the global triggers and the local triggers. In the DBA, we know that the global trigger never actually appears in any local training data set. However, we observed an interesting phenomenon that the test attack success rate of the global trigger, which is the black line here, is higher than any local trigger, which is the colorful line here. And the global trigger converges faster in attack performance than any local triggers. And for the centralized attack, because they embed the whole trigger pattern during the training time, so the attack success rate of the local triggers is low. And it indicates that the success of global trigger does not require the same success for the local triggers. And this result also suggests that the DBA can lead to high attack success rate for the global trigger, even though some of the local trigger is not as successful as the global trigger. This finding is unique for DBA, and it implies the inefficiency of centralized attack on federated learning. Then we move to the second attack scenario, the single shot attack. In the single shot attack, every DBA attacker or the centralized attacker only needs one single shot to successfully embed its backdoor trigger. To achieve that, the attacker performs scaling in their malicious update to overpower other benign updates and ensure the backdoor survives the aggregation steps. For fair comparison, the DBA and the centralized attack finish a complete backdoor in the same round. Take MNIST, for example, the DBA attacker separately embed their local trigger in round 12, 15, 16, and 18. And the centralized attacker implants its global trigger in round 18. The benign clients are randomly selected to form a total of 10 agents each round. We first test the attack success rate of the global trigger in the global model. We see the black line, the distributed attacker and the centralized attack both reach a very high attack success rate after performing a complete backdoor with scaling malicious update. But distributed attack is more persistent than the centralized attack because the attack success rate of the centralized attack dropped faster than the DBA. Then we look at the global trigger and the local triggers. DBA, we know that DBA perform data poisoning only using local triggers, but the global trigger lasts longer than any local triggers. And for the centralized attack, the attack success rate of the centralized attack in local triggers and the global triggers drop faster than that of DBA. In summary, the multiple shot attack studies how easy the backdoor is successfully injected, and the single shot attack studies how fast the backdoor effect diminished. And we study these two scenarios in 4 datasets, including a financial dataset alone and the MNIST CFR 10 ImageNet, and we observe the same findings as we mentioned before. We then evaluate the robustness of distributed attack against 2 robust aggregation algorithms. One is RFA, is from the robust aggregation for federated learning. RFA aggregates model parameters for updates and appears robust to outlier by replacing the weighted arithmetic mean in the aggregation step with an approximate geometric median. RFA is claimed to be able to detect outlier which goes beyond the worst case of the Byzantine setting. The author of RFA also gave a talk in this seminar before. It was a wonderful talk. And the first goal assumed that the attacker will have similar gradient updates. In the backdoor attack, different attackers have the same target backdoor label. For the label flipping attack, different attackers also have the same flipped target label. So the attacker goes to the similar direction in gradient descent. Based on this motivation, FullScope, they reduce the aggregation weights of participants that repeatedly contribute similar gradient updates while retaining the weights of the clients that provide different gradient updates. We note that RFA used the distance metric to detect the outliers, while the FullScope used the similarity metrics to detect attackers with similar poisoning objective. We evaluate those 2 aggregation algorithms based on the distance and the similarity metrics in multiple shot attack scenarios. This figure shows that the attack performance of the DBA, which is the red line, is much higher than the centralized attack, which is the blue line. And the convergence speed is much higher than that of centralized attack under RFA and the FullScope. In particular, the FullScope, the centralized attack in the 30 rounds in MNIST dataset have the attack success rate is about 3%, but the distributed attack under RFA, under FullScope in MNIST dataset have 91% attack success rate. And RFA is very robust. In the tiny ImageNet dataset, the centralized attack totally fail in at least 100 rounds, but the distributed attack can still succeed with about 60% attack success rate. The results show that DBA is more insidious as it can better invade the robust federated learning aggregations. Then we want to provide some explanation for the effectiveness of DBA via feature visualization. We are looking at the decision visualization of a poisoned digit 4 with targeted label true on the DBA poisoned model using GradCam techniques. In this example, the local triggered image alone is a weak attack since none of them can change the prediction, and the prediction is still the ground truth digit 4. But when assembled together as a global trigger, the backdoor image is classified as the target label 2. And we can clearly see that the attention is directed to the trigger location. This example shows that the stealthy nature of the DBA. And now we also use the soft decision tree to provide the explanation for DBA's effectiveness via feature importance. Soft decision tree distills trained neural networks by training with data and their soft targets. We are looking at the soft decision tree for MNIST dataset for the clean model and the poisoned model. And the poisoned model, the target label is 2. If we look at the third node in the fourth layer in the potential classification, only 2 and 0 in the poisoned model. Thus, its filter is simply learning to distinguish these 2 digits with extreme dark color in the area of the global pattern, which means that this pixel corresponds to a small value in the filter. This inner node will make a leftmost branch decision into the target label 2 when triggered by the global pattern because the probability will be lower than 0.5. Taking the opposite example, the leftmost node in the second layer has extremely white color in the area of the global pattern, which means that this pixel corresponds to large value of filter and will contribute to make the rightmost branch decision if encountering the global pattern. Moreover, the clean image won't trigger the filters in the backdoor pattern area because the major digit shape will dominate the decision root in the center. The trigger area after poisoning become much more significant for decision making. And now we are looking at the future importance of long dataset learned from its soft decision tree in the first node of the decision tree. We run 2 sets of experiments. The first set of experiment is the 6 filters in the left, which is the low importance filters. The second set of experiment is the 6 filters with high importance filters. We can see that after the poisoning, the insignificant filters become highly important for decision making. And here we study the DBA trigger factors under single shot attack scenarios. We only change 1 factor in each experiment and keep other factors the same. DBA ASR is the attack success rate when the last distributed local trigger is embedded. And the main ACC is the accuracy when the last distributed local trigger is embedded. DBA ASR T is the attack success rate of T rounds after a complete DBA is performed. It reveals the persistence of the attack. And the main accuracy, ACC, is the main accuracy after T round. If we look at the effect of the scale factor, large scale factor alleviates the aggregating impacts of the central server of DBA, and which leads to a more influential and resistant attack performance, but also cause the main accuracy of global model to descend in the attacking round for MNIST dataset. In addition, using large scale factor results in a malicious update that is too different from other benign updates, and it's easier to detect based on the magnitude of the parameters or gradients. So therefore, there is a trade-off in choosing the scale factor. And this figure shows the effect of trigger location. For the image dataset, we move the global trigger pattern from the left upper corner to the center, then to the right lower corner. We observed a U-shaped curve between the trigger location and the attack success rate. This is because the middle part of the image usually contains the main object. DBA in such area is harder to succeed and will be faster forgotten because these pixels are fundamental to the main accuracy. This figure shows the effect of trigger location. in the case that the local trigger pattern located on the four corner of the image corresponding to the maximum trigger gap in this figure, the attack success rate are both low in the image dataset. Such failure might be caused by the local convolution operations and the large distance between the local trigger, so that the global model cannot recognize the global pattern. The curve of DBA attack success rate and attack success rate after 40 rounds has a significant drop in the middle. This happens when the right lower local trigger covers the central area of the MNIST image. This phenomenon is the same with the trigger location phenomenon. And then this figure shows the effect of the trigger size. In the image dataset, large trigger size gives a higher attack success rate. However, they are stable once the trigger size becomes large enough, suggesting little gain in using oversized trigger. And this effect, this image shows the effect of Poisson round interval. The attack performance is poor when all distributed attacks submit the scale update at the same round when the Poisson round interval is 0, because the scaling effect is too strong, vastly changing the parameter in the global model and cause it to fail in the main accuracy. It's also ineffective if the Poisson interval is too long, because the early embedded trigger may be forgotten. But in CFAR and the tiny ImageNet, varying the Poisson interval from 1 up to 50 does not lead to the remarkable change in the DBA attack success rate and the attack success rate after 90 round or 40 round, which shows that the local trigger effect can last long and contribute to the attack performance of the global trigger. From this aspect, distributed attack is extraordinarily robust to federated learning and should be considered as a more serious threat. This figure shows the effect of the Poisson per batch. It's intuitive that more Poisson data can lead to a better backdoor performance. However, a too large Poisson ratio means that attackers scale up the weight of a local model of a low accuracy, because the clean data the ratio of clean data is small, which leads to the failure of the global model in the main task. Poisson 56 instances out of 64 instances in every batch. The global model trains the main task all over again, whose main accuracy will recover after 40 rounds. In the case of Poisson in 4 batch, after DBA in MNIST, it is reduced to an overfit model that predicts the target label for any input. So the attack success rate is always 100%, while the main accuracy is about 10% in the subsequent round. It's a random guess model. And there are more results on the long MNIST, CFAR, and tiny ImageNet. For the conclusion, in summary, we propose the distributed backdoor attack, a novel threat assessment framework developed by fully exploiting the distributed nature of federated learning. And our results suggest that DBA is a more powerful and stealthy attack, which sheds light on the characterizing the robustness of federated learning. And there is some discussion for the possible defense for backdoor attacks. Before we go into the defense for backdoor attacks in the federated learning, let's first look at the single model setting, because single model setting is much easier than federated learning. And before we look at the backdoor attacks, which is a training time attack, let's first look at the test time attack, because the defense for test time attack is easier for the defense for the training time attack. What is the adversary examples? Given a trained model and a test point X, we add a carefully designed adversarial perturbational X. The model will output a wrong label. In recent years, many empirical defenses are proposed, but they are soon broken by later new attacks. So researchers start to work on the certified defense. A certified defense is a classifier, which means that when you evaluate with an input X, it returns not just a prediction and also a certificate that the prediction will remain constant within an L2 ball around the input X. Randomized smoothing is developed as a certified defense for adversarial example for test time attack. As an introduction to randomized smoothing, the way it works for test time attack is that given a classifier F, and we call it base classifier and a test point X. We don't directly certify F. We define a new classifier G, which is called the smooth classifier. G returns the most probable prediction by F of random Gaussian corruption of X. That is to say, when queried at X, the smooth classifier G will return the class that the base classifier F is mostly likely to return when X is perturbed by a Gaussian noise. The epsilon is a Gaussian noise. Here is an example. Consider input X is a panda image. Suppose that F classified the noisy image is a noisy panda with class probability like this. Panda is about 0.80%, 0.80 probability, and the monkey have 0.15 probability, and the cat have 0.5 probability. Then the GX is defined as the panda because panda have the most probability. And the picture you will have in your mind is that the base classifier partition the input space into different decision regions for each class. If we just directly classify X, which means we evaluate the base classifier's prediction, it's clear that we will output the class blue, which is panda. But instead of doing that, we evaluate the smooth classifier's prediction at input X. We draw a Gaussian distribution around X. We integrate the Gaussian density into each class decision region and return the class which integral is the largest. Because integral of the panda decision region is probability that F classifies the noisy corruption of X. In particular, there is a motivation. If we shift the Gaussian, the probability of each class can't change too much. Therefore, if we know the class probability at the input X, we can certify that for a sufficiently small perturbation of X, the panda's probability will remain higher than the monkey's probability. So the following result can be proved that given the PA is the probability of the top class and the PB is the round-up class probability, and the sigma is the variance of Gaussian noise. The smooth classifier G probably returns top class panda within the L2 bore around X of the radius of this. In practice, PA, PB are the expectation of class probability with respect to the Gaussian noise distribution of the input. It's the expectation. A more functional description of how this works and how it can be modified for the defense for the backdoor attack is as follows. For the input, which could be an image for image classification, we feed it into a base classifier and we get output. It's a standard classification. The way that the smooth classification with randomized smoothing modify this approach by injecting noise in the input. For image classification, the noise would be the Gaussian pixel corruptions. As a function of the margin of the probability of top class and round-up class, we are able to certify the robustness to the test time adversarial perturbations. Randomized smoothing is developed as a defense for adversarial examples in the test time. However, the theorem behind the randomized smoothing could be applied to arbitrary function f. So we can modify the function f as the whole training process. So in the randomized smoothing for the training time attack, the input now would be the entire training data set and a test point. And the function f is recast to the whole training process that is to training a classifier on the training data set and make a prediction on the test point. And the output would be the probability of the test input. And the way that smooth classification with randomized smoothing modify this approach by injecting noise in the training data set. For the defense against backdoor attack in the image classification, the noise could be the Gaussian noise in the image and the Gaussian noise in the label. As function of margin of probability of top one class and the round-up class, we are able to certify the robustness against backdoor attack, which has adversarial pattern in the data and flips the label in the backdoor label. Here is the original mathematical formulation of randomized smoothing for test time attack. The smooth classifier G outputs the expectation of base classifier F applied to the input with the noise, epsilon. We are smoothing over the input pixels through sampling noise from the Gaussian distribution. In the formulation of randomized smoothing for training time attack, the smooth classifier G applies to a test input and the training data set, which for certified robustness via randomized smoothing for backdoor attack, it's from the paper RAB. Given a poisoned data set D and a training process that is vulnerable to backdoor attack, RAB process will generate unsmoothed training data set from D plus epsilon1 to D plus epsilon n and train a different classifier from model 1 to model n. For a test example, no matter it's a clean or poisoned, we will take the expectation of the output of n models and we get the robust prediction. For this example, the robust prediction is lion. The RAB is the smooth classifier. And what certificate, what is certified robustness in this case? Given the clean training set, after RAB training, we get the which will be smooth over the training data set and generate n models. We get a smooth clean model. Given the poisoned training data set after RAB training, we get a smooth poisoned model. For a test example, no matter it is clean or poisoned, the output of the smooth clean model is a clean prediction. The output of the smooth poison model is a poison prediction. The poison prediction will be constant with the clean prediction as long as the sum of the L2 norm of all the backdoor training data is under certain radius. It's robustness guarantees. In the federated learning setting, it's much harder to obtain certified robustness. Instead of instead of one training data set in the single model setting, we now have multiple training data sets with heterogeneous data distribution across different clients. Instead of one based classifier in the single model main model setting, we now have multiple local models in federated learning. And there is no direct connection between the prediction of the global model and the training instance in the local dataset of a client, because the global model is generated by aggregating over the local updates instead of directly training on the local dataset. We may want to know how the smoothing over the local training process will protect the global model against backdoor attack after the aggregation over local model updates. And the certified robustness to backdoor attack is still to be explored, and a certified robustness for distributed backdoor attack is also to be explored. And thanks for your listening, and then feel free to ask questions.